Okay, so good afternoon, everybody. I'm really glad to welcome you to this first session of Best Student Paper. So this year we have selected 8 papers to compete for this Best Students Award. So we'll have 4 presentations today and 4 presentations at the same time slot tomorrow in the afternoon at 5 p.m. in European Western time, so that mixed the time slots, something which is quite difficult to follow given numerous presentations we have in this conference. So I will really briefly present the speakers we have today. So as I said, we have 4 presentations today. So we'll start with Olivier Ruhnau. Hi, Oliver, sorry, not Olivier, Oliver Ruhnau from Hertie School. Then we'll move to the presentation from Diego Kaenzig. Sorry if I miss saying your name. So Diego Kaenzig from the London Business School. And then we'll give the floor to Leopod Monjoie, which is easy for me since Leopod is French. So Leopod works at the University of Paris Dauphine and also at the French Transport System Operator, for RTE, for one who knew RTE. And then we will give the floor to Federico Accursi. Yes, Federico is there as well, from the University of Navarra. So, and Federico wears his mask, so we respect the barrier. Hello, Federico. So you will all have 20 minutes to present, and your presentation will be followed by about, let's say, 5 or 10 minutes of questions and answers from the audience and for the other students. So with no more words, I give you the floor, Oliver, for about 20 minutes.
Thank you. I will just share my screen. Like this. And yes, I think you can hear me and see my slides. Can you? Great.
Everything is fine.
So yes, thanks for inviting me to present my paper, my work on how flexible electricity demand stabilizes wind and solar market values. And I will look at a specific type of flexible electricity demand, which is hydrogen electrolyzers. The paper I've submitted is also available as a working paper. So if other participants want to look up the details, please feel free to follow the link in the presentation, which I also uploaded. So why is it interesting to look at stabilizing, or what could stabilize market values? Well, it's because it's not only the cost of renewable electricity, but it's also the market value which will determine how many renewables we will have and at what cost we will have them in future electricity systems. And here there are previous studies working on this. And here you can see what they find is that the more renewables you introduce into electricity markets, the lower is their market value, because whenever they produce, they will depress their additional supply, which comes at zero marginal cost, will depress electricity prices, and that's what reduces their market value. And that's a pity, because even though costs decline, we will have, of course, we will have an increase in the optimal share, but it's not set. We cannot take that for granted that at one point renewables will take over the system. And if we want to go beyond that share, for example, to reduce climate impact, then we will have some support costs that policymakers must provide to increase the share of renewables even further. And in practice, that leads to 2 questions. First, from an investor's perspective, the question is, can renewables earn back their fixed costs on the free market? And second, more the policy perspective, will there be an ongoing need for renewable support schemes in the future? And previous studies have also looked at possible mitigation measures for this value decline. For example, they have looked at storage, transmission, or low wind speed turbines, which could, and they found that can increase the market value, and that can slow down the decline in market values. But so far, nothing has been found that could permanently stop the decline in market values. So my question is, can hydrogen, green hydrogen, or more generally hydrogen produced from electricity, can that change these previous findings? And that's of course interesting to look into right now, because there's a lot of political attention to this topic. Here, for example, the national German hydrogen strategy and the European hydrogen strategy, but they are different. There are other countries also looking into this, both as possible importers, exporters, producers, etc. And second, there are some studies claiming that, well, also for this technology, not only for the renewables, but also for hydrogen electrolyzers, which could transform electricity into hydrogen, the cost could decline. So here, so far, many studies have looked into the competitiveness of green hydrogen against other alternatives, other colors of hydrogen, other alternatives to produce hydrogen from different sources. But in this study, I will turn this perspective around and look at how could hydrogen also improve and change the competitiveness of renewables. So the question is, can flexible hydrogen electrolyzers stabilize renewable market values? And I will look into that with multiple methods. First, I will introduce or expand existing theoretical frameworks to include the optimal dispatch and investment in electrolyzers. On this basis, I will derive an analytical formula for the minimum market value as a function of very few hydrogen parameters. I will quantify this value taking into account uncertainty using Monte Carlo analysis, and then in the end complement these rather simplistic estimates with a more detailed electricity market model, and finally draw some conclusions and discuss policy implications. So let me start with a theoretical framework, and let me start with the dispatch perspective. The value of renewables has been analyzed using the merit order model, and that holds that power prices equal the marginal cost of supply. We can see this here in the first example. We have the step upward sloping supply curve, and where that intersects with the demand, which is usually assumed being inelastic, so independent of prices, then the marginal cost of the generator will set the price, and that's except for scarcity prices, which I will not look into in more detail. And when renewables are now introduced in the market, whenever they are available, whenever they produce, their low cost, low marginal cost, or close to zero marginal cost will shift outwards the supply curve, and thereby depress market prices, possibly even to zero. And that's here in the second example, where renewables exceed demand. We have negative residual load and zero prices. And that's without electrolyzers. And now we can think in the same framework, introducing electrolyzers and how these will change the picture. And we can think of the optimal dispatch of electrolyzers, which is they will turn on whenever the electricity price is below what are their product revenues, which per unit of electricity. So that depends on the hydrogen price, the variable costs they have, and the efficiency transferring electricity into hydrogen, and then supplements which they may pay on top of the wholesale electricity price, which is displayed in this graph here. And then we see this the step also in the demand function, where the demand increases below this willingness to pay by the electrolyzers, which I also call the electrolyzer dispatch price. And as a result, we can say that electrolyzers can increase, or in this case, even set the electricity price. So that's something in addition to what is the common sense right now, that it's always the marginal cost of generators. But here we can say, if we have such flexible demand, could also be the willingness to pay of demand, which could set electricity prices in addition to scarcity prices, where this is well accepted. And here I make a simplification, and that's why I think hydrogen is a good example to look into, because here I assume that there's a constant hydrogen price, so constant over time. And here, as a simplification, all the electrolyzers get the same price. And I will relax the simplification later on. But for now, I think it's justified because hydrogen can be stored at very little cost. So we can assume, like similar as for natural gas, we can assume there's a rather constant price when compared to the hourly fluctuation of electricity prices. So that was the optimal dispatch of electrolyzers, and we can now zoom out and look at the whole year of electricity prices, taking the price duration curve to see what's the optimal investment in electrolyzers. First, in the price duration curve, we can look at what's the impact of renewables, and that is the more renewables we have, the lower our prices in times when there are many renewables, when there's much renewable generation, such that the price duration curve, which are the electricity prices is sorted by price for 1 year, they will decrease, and also the slope of the electricity prices can be expected to increase. And we will have quite a few of zero electricity prices, as we've seen before with the examples here. And now what happens if we think of electrolyzers? We can again take the electrolyzer dispatch price, which is their product revenues, draw this line into the price duration curve, and then we can think of that the annual margin of the electrolyzers, that's the difference between the electrolyzer dispatch price, their revenues, and the electricity prices. So they will start producing from this hour onwards, and we have, and that's their margin, basically the area between the dispatch price and the price duration curve. And if that's larger than their annualized fixed cost, then they will start investing, and those additional investments, those new electrolyzers will, as we've seen before, increase electricity prices or set electricity prices. And such investment will happen up to the point where the margin which remains is exactly equal to the annualized fixed cost of electrolyzers. So that's the market equilibrium. And that brings me, and we will have still some zero prices despite electrolyzers, because they need this margin. They need these low prices to earn back their investment costs, the electrolyzers. And that brings me to the argument of this paper, which is that flexible electrolyzers balance the value decline of renewables, because variable renewables will depress electricity prices. But then once these prices fall below a certain threshold, this will trigger additional additional investment in flexible electrolyzers, and they will stabilize prices. So whenever there's an additional wind farm installed, there will be someone else installing on a market basis another electrolyzer. So on this basis, this argument can be used. I use this argument to derive an analytical formula for in this equilibrium for the minimum market value. And that comes with two conservative assumptions. First, I ignore these potentially higher prices, and I say, as a simplification and as a conservative assumption, electricity prices will either equal to the electrolyzer dispatch price, or they will be zero. So also here I make a bit of a simplification, and then I come up with a maximum duration when prices are zero throughout a year. And the second conservative assumption is that there's a perfect correlation, a negative correlation between renewable generation and prices, which means that the hours or the times of the year where renewables produce the most, they will end up with zero prices, zero revenues. But then I can say that the remaining renewable production, they will receive at least, and again, that's a conservative assumption, the electrolyzer dispatch price. And with that, I come up with a formula for the minimum market value of renewables, which depends exactly on this electrolyzer dispatch price, minus a term which depends on the fixed cost of electrolyzers, And here we can see that depends on the renewables, and that is the average capacity factor of renewables during hours with zero prices divided by the annual average capacity factor of renewables. And we will see how that plays out in a minute. Because I can use this formula now to quantify this minimum market value in the Monte Carlo analysis, taking into account the uncertain parameters which I need to compute this simple formula from before, which are quite a few parameters, which is for example the hydrogen price, which I need to compute the dispatch price of electrolyzers, and the capital cost of electrolyzers to compute the annualized fixed cost, the efficiency, and so on. And here I've looked into the literature and determined a sensitivity range for 2050, and I use the Monte Carlo assuming a uniform distribution within this range to quantify the distribution of the minimum market value. Second, I use renewable profiles. I take them from a data set covering 34 European countries and 10 different weather years, making some assumption on the future capital stock of renewables and future technologies placing, and so on. And here I randomly select between these profiles in the Monte Carlo simulation. And first, I will assume to abstract from from policies in different countries, I will assume that there's no demand supplement at all on wholesale electricity prices, and I will relax that assumption in a minute. So that's the result for the Monte Carlo simulation. Here we can see that there are that's the distribution of the minimum market value for the different technologies: solar PV, wind onshore, and wind offshore. And the first thing we can see is that these estimates are significantly above zero. So we can say with quite some high probability that because of flexible electrolyzers and because of this possibility to use renewables to make some hydrogen when they are available, we can say that the market value will likely not fall to zero. Second, we can compare the number here for the minimum market value, the numbers, to projected levelized cost. And we can say that for solar PV and wind onshore, these are in quite a similar range. So we can say that it's quite likely also that there's a high chance that we will see wind and solar investment on a market basis. For wind offshore, it's a bit below that, but then again, for all renewables, the distribution is quite wide, so it's also not. It could also happen that this is the case for offshore, just on the basis of hydrogen electrolyzers. And I've also run a sensitivity on the most important parameters which drive this minimum market value. And here we can see that the higher the assumed hydrogen price is, the higher is also the minimum market value of renewables. We can see that if the electrolyzers capital cost, investment costs decrease, we also see an increase in market values, and also we see that they are quite harmonized at such low cost of electrolyzers. And finally, we see that so far I've assumed that there is no supplement that electrolyzers must pay on wholesale electricity prices. But here we can see that once we introduce such a supplement, which could be a taxes or levies or grid fees, we see that this minimum market value decreases because hydrogen electrolyzers are not consuming as much, setting the price at such a high level, or they are just not as much, there's not as much hydrogen investment. So far, that's quite simplistic, assuming only one technology, hydrogen electrolyzers, and seeing how that interacts with renewables. And I think that has the strength that we can understand that renewables, the competitive of renewables is a function, or amongst others, how that relates to flexible electrolyzers. And that's quite agnostic about many other power system parameters, so about other types of demand, supply, and storage. So the results can be quite easily generalized. But of course, that has some limitations. First of all, I'm calculating the minimum market value. So in the end, it's the question, what is the actual market value then? I haven't considered other flexibility options. In particular, I haven't considered other types of flexible electricity demand. I have assumed this constant hydrogen price and unrestricted transmission between renewables and electrolyzers. And some of these limitations, I will address them. I will relax the assumptions, the simplifications in the last step using an electricity market model. So here I'm using a model which has been there before, the electricity market model EMMA. I use that to calculate the long-term market equilibrium for greenfield investment and dispatch. I calculate I set exogenously how much wind and solar will be invested, the solar share, the renewable share in the market, and newly I introduce endogenous electrolyzers and investment and dispatch, which has not been there before in the model. I'm now fixing the uncertain parameters from before to the center estimates, for example, the hydrogen price and the investment cost of the hydrogen electrolyzer. And then I'm using Germany plus 4 neighboring countries, and I'm using the profiles for these countries for the year 2010. And then I'm comparing 3 scenarios, or actually 4 scenarios, 1 scenario without electrolyzers, 1 with flexible electrolyzers, 1 where they are perfectly flexible in the sense that there is still a constant hydrogen price. I'm not accounting for the cost of hydrogen storage. That's what I do in the second scenario, where hydrogen must be supplied at a constant rate, for example, to serve some industrial processes. So flexibility is still possible, but it comes at the cost of hydrogen storage. And finally, 1 inflexible hydrogen scenario where I assume there's no storage. And here you can see the results. The colorful lines here in yellow and blue, that's without electrolyzers. And we see here that the market value indeed falls close to 0 for all the different technologies. Second, with the perfectly flexible electrolyzers, that's the solid lines here, we see that the market values converge above the analytical minimum, so that supports the approach I've used before. Once I consider that there is some cost, but the costs are very much lower than for electricity, there's some cost to store hydrogen, we see that the market values drop a bit. But for wind, they still, or for all technologies, they still seem to converge. And for wind, they are a bit higher than what is the analytical minimum still. And finally, for the inflexible scenario, we see that market values fall quite a bit lower, which really means that flexibility is key to stabilizing the market values. So let me conclude. If electrolyzers can stabilize market values, we may end up with a much higher optimal share of wind and solar. These may be reached in competitive markets without direct policy support. Although regulation may still play a role. For example, we've seen that the supplement electrolyzers pay on wholesale prices play a role. And finally, some conclusions on flexible electricity demand. That's crucial and really makes the difference when analyzing variable renewables. Hydrogen electrolyzers may also be feasible on a market basis, triggered by renewables, triggered by low electricity prices. That's an ideal type of flexible electricity demand with distinct characteristics. Nevertheless, I think the presented framework can be extended and adjusted to cover other flexible electricity demand. And in the end, the different types of flexible electricity demand will compete with hydrogen electrolyzers and for using renewable electricity, and jointly contribute to stabilizing market values of renewables. And with that, thanks for your attention, and I'm looking forward to your questions and feedback.
Thank you very much, Oliver. We have a few minutes for discussion, so you can ask your question to Oliver either directly turning on your mic or through the chat room. Any question from the audience?
Yes, I would have one. Hi, Oliver. Thank you for your presentation. Interesting research. My question is, have you assessed how green the hydrogen is that you still produce at the end? Because if you consume or if you inject electricity from the grid, especially in Germany, there's still the risk that the hydrogen that you're actually injecting in the electrolyzer is not that green.
Thanks for the question. I think that's very interesting, and it's not so easy to answer because it depends, like, what's the definition of hydrogen being green. The aim of this paper is to show that even though I do not impose a constraint that hydrogen can solely be produced based on renewables, we will see a positive interaction between hydrogen and renewables on a market basis. In addition to that, we can see, maybe not sure if it's worth sharing the slide again, but maybe you have to still in mind the declining market values, and you could see that it's not only the market value being increased through flexible electrolyzers, but it's also the market share. We're reaching much higher market shares in the end because there's much less curtailment of renewables. So that's another indicator that this is very green, yeah. But I haven't imposed, and it's hard to tell whether it's 100% green, of course.
All right, thanks.
Welcome.
All right. Any other question? Yes.
If it's still possible. Thank you, Olivier, for the presentation. Just maybe one question, but I might have misunderstood. So the cost of hydrogen, like how the price they get when selling to the hydrogen market, whatever that might be, that is an exogenous parameter in your model. Is that correct? But at
Yes, that's correct. Mm-hmm.
At the same time, wouldn't that be a sort of an issue, because somehow that price could also be driven by the price of electricity and not the other way around? Or don't you see any issue there?
Mm-hmm. Mm-hmm. So what I've done in the paper is checking whether the amount of hydrogen that is produced is in line or exceeds or is below what is the projected demand for hydrogen, and it's actually well in the range of what people project for hydrogen. So I conclude that there's no risk of this additional hydrogen supply depressing the value of hydrogen to a much lower level, because it is needed in so many sectors, not only the electricity sector for long-term storage, but also the other sectors. And then I use this 1.5 to 2.5 euro per kilogram of hydrogen, which is a rather low, so rather conservative assumption. But of course, it's a wide range, but still it's conservative when compared to like net zero scenarios, because then the need for hydrogen is actually quite high.
Okay, thanks.
Welcome.
Okay, maybe a last question, Oliver, very shortly. In your paper, you are looking ahead in the year 2050. We can assume that at this time, the market share of renewable will be close to 100%. So is your model robust and your results consistent with this kind of electricity sector, where the electricity price from the short-run marginal cost is mostly close to zero, most of the time close to zero?
Mm-hmm, mm-hmm. I think so. What also drove my research is comparing this market value analysis and this market thinking that the electricity price must be zero in such a high shares of renewable system. But then again, we have, on the other hand, scenarios with 100% renewables saying, well, that's economically feasible. And the argument here is that the price must not be zero, because there will be so many electrolyzers or other kinds of flexible demand, and they will set the price actually above zero. So that's my conclusion here.
Thank you very much, Oliver. There is some parameter that you miss in your study. It's the carbon price. You know that the carbon price are increasing, especially in Europe. That's something that tends to push the electricity price up. So that's the question that we'll address, Diego. So Diego, the floor is yours for 20 minutes.
Thanks, Boris. That's the perfect transition to my paper. So let me try to share my slides. Can you see my slides?
Yeah.
All right, so perfect. First of all, let me also thank the organizers for including my paper on the program. I'm very excited to be here today and be part of this great session and to be able to present my work on the economic consequences of putting a price on carbon. The looming climate crisis is probably the single greatest challenge of our time, and we can learn about it almost every day. For instance, when we read the newspapers and learn about the extreme weather events around the world that have become much more frequent because of climate change. On the current path of emissions, global average temperatures are set to increase by over 3 degrees Celsius by the end of the century, and this in turn will likely have devastating effects on the environment, on human health and livelihoods, and also the global economy. Now, in theory, we know relatively well what we can do to address this issue. Going back to Pigou, this is a clear externality, so we have to internalize the cost of polluting by putting a price on emissions at the level of the social cost of polluting. However, this has proved to be very difficult to implement in a globalized world with many stakeholders. More progress has been made at the national level, with several countries having enacted carbon pricing policies either in the form of carbon taxes or cap and trade system. But because these policies haven't been around for that long, still relatively little is known about the effects of these policies both on emissions and the economy. In particular, it is unclear a priori how effective these national policies are in reducing emissions because of carbon leakage, for instance. And there is also the question about costs, because as we know from the literature on discretionary tax changes, these policies may have adverse effects on economic activity, at least in the short run. In this paper, I provide new evidence on this matter from the European Emissions Trading Scheme, which is the largest carbon market in the world, and also, as Boris has said, has been in the news recently because the prices have increased significantly this year. And I will exploit institutional features of this market in combination with high-frequency data to estimate the dynamic causal effects of carbon pricing. The European Emissions Trading Scheme is a cap and trade system, so an overall cap is set on emissions, and within this cap, emission allowances are allocated and then traded. So there is a market price for carbon, and there exist also very liquid futures markets. At the same time, establishing the European Emissions Trading Scheme has been a process, and the regulations in the market have changed considerably over time. And this provides me with a very nice setting for identification. The idea is to isolate some exogenous variation in the carbon price by measuring the price change in a tight window around regulatory policy events concerning the supply of emission allowances. And in the next step, I will use this as an instrument to estimate the dynamic causal effects of a structural carbon policy shocks. So I'm really concerned here with the macroeconomic effects, but also later heterogeneous effects of these policies. To give you a preview of my results, I find that carbon pricing has significant effects on emissions and the economy. A shock tightening the carbon pricing regime leads to a significant increase in energy prices and a persistent fall in emissions. However, this does not come without cost. Economic activity falls and consumer prices increase. Importantly, these costs are not borne equally across society. I find that poorer households lower their consumption expenditures significantly and persistently, while richer households are barely affected. In the interest of time, let me skip the related literature and start right into the paper by giving you some more detail on the identification design and the European carbon market. This market was established in 2005 and covers around 40% of overall EU greenhouse gas emissions. It is a cap and trade system, as I said, so there is an overall cap which is reduced each year to ensure that emissions fall. And within this cap, emission allowances are allocated, and they're being allocated by different means, in particular free allocation and auctioning. Now, at the end of every year, the companies covered by the system must surrender sufficient emission allowances to cover their yearly emissions, and this is enforced with heavy fines. Allowances are traded on secondary markets, both spot and futures markets. So if a company, for instance, is short of emission allowances at the end of a year, it can buy additional allowances on these markets. Establishing the EU ETS did not happen overnight. It was more of a learning by doing process. Particularly, it was established in 3 main phases. But even within these phases, the rules have been updated continuously over time. For instance, to address issues encountered in the market, to expand the coverage of the system, both in terms of gases and sectors covered, or to improve market efficiency. So there are really lots of regulatory events in this market. Here you can see the carbon price over the 3 phases that I'm considering in this paper. And what I want you to take away from this figure is that the policy was successful in establishing a non-negligible price on carbon in the EU. However, for an extended period of time, this price was at rather low levels, and this was because of the global financial crisis and the subsequent recession, which led to a reduction in emissions that was much larger than projected, and thus there was an oversupply of emission allowances in the market. In the next step, I collected a comprehensive list of regulatory update events. These can take the form of decisions of the European Commission, votes of the European Parliament, or judgments of a European court, for instance. As I've said, of key interest in this paper are regulatory news on the supply of emission allowances. So news regarding the free allocation of allowances, regarding auctioning, for instance, the timing or the quantities to be auctioned, and also the use of international credits. In this way, by going through the official journal of the European Union, as well as the Climate News Archive of the European Commission, I was able to identify 113 such events in the sample spanning the period from 2005 to 2018. Here you can see a little excerpt of these events that I collected. So some takeaways from this is that these events are quite diverse. A key event in this list occurred in April 2013, when the European Parliament voted against the Commission's backloading proposal. To give a bit of context, this was related to this oversupply in the market because of the global financial crisis. So the Commission wanted to postpone, to backload the auctioning of new allowances, and in the first instance, the European Parliament voted against this proposal. Now, based on these events, the idea is then to construct a series of carbon policy surprises by measuring the price change in these EUA futures prices in a tight window around the events. In particular, I measure the price change as the percentage change in the futures price on the event day and the last trading day before the event. And in the next step, I aggregate these daily surprises to a monthly surprise series, because ultimately I'm interested in the effects on monthly indicators. Here you can see the resulting series of carbon policy surprises. And we can see that some of these events led really to massive changes in the carbon price. For instance, the vote against the backloading proposal that I talked about before caused the price to collapse by over 40%. So this was a really sizable change. There were also a number of other large events, but importantly, what I want to stress here, my identification strategy does not depend on these very large events. Excluding them does not change my results considerably. I only lose a bit of statistical significance. I also perform a number of diagnostic checks on this surprise series. In particular, I confirmed that it accords well with the narrative account on some key historical episodes. I show that it is not autocorrelated. I also find that it is not forecastable by past macroeconomic and financial variables. And I've also verified that it is uncorrelated with other shock measures from the literature, for instance, proxies for oil, uncertainty, or fiscal shocks. So I hope that I have been able to convince you that this carbon policy surprise series has some nice properties, but I will still argue that it is an imperfect shock measure. Therefore, I will not use it as a direct shock measure, but as an instrument to estimate the dynamic causal effects on emissions and economic activity in the context of a time series model. For those familiar with this literature, I will use 2 complementary approaches: the external instrument approach and the internal instrument approach. And for estimation, I will rely on VAR techniques because the sample is relatively short So this is a good way to estimate the effects of interest because it provides a parsimonious representation of the data. My baseline specification includes 8 variables consisting of a carbon block, which includes the energy component of consumer prices and total greenhouse gas emissions, and a macro block, which contains headline consumer prices, industrial production, unemployment rate, the policy rate, stock market index, and the real effective exchange rate. And the estimation sample spans the period from 1999, when the euro was introduced, to 2018. All right, so after all these details on my approach, we can now move to the fun part, and I can show you some results. But first, as in any instrumental variable analysis, we have to look at the first stage first. Therefore, I perform a weak instrument test. The F statistic is around 21, and thus significantly larger than the critical value. Therefore, I find no evidence for weak instrument problems, and I proceed with standard inference. In these figures, you can see the results of the baseline models. For interest of time, I will focus here on the external instrument approach, but you can see that both approaches produce relatively similar results. So here you can see the impulse responses to a carbon policy shock normalized to increase the energy price component of consumer prices by 1% on impact. So we can see that this carbon policy shock leads to a significant increase in energy prices and a persistent fall in greenhouse gas emissions. Therefore, the policy appears to be successful in achieving its goal of reducing emissions. However, this does not come without cost. Consumer prices also increase, the pass-through is around 15%, industrial production falls, at least temporarily, and the unemployment rate rises persistently. Looking at the monetary policy rate, we can see that monetary policy doesn't seem to respond significantly to the shock. Stock prices fall, but the response is not very front-loaded, so it seems to respond more to the fall in activity rather than having like an immediate effect, and the real effective exchange rate depreciates significantly. So overall, these results illustrate the trade-off between reducing emissions and thus the future cost of climate change and the cost in terms of lower economic activity today. We can also look at the historical decomposition and the contribution of carbon policy shocks over the sample for some key variables of interest. So here you can see the historical decomposition of greenhouse gas emissions growth, which are depicted here in orange. And in black, you can see the contribution of carbon policy shocks. So it is apparent that carbon policy shocks have contributed meaningfully to the historical variations in greenhouse gas emissions, but importantly, they do not account for the large fall in emissions after the global financial crisis, which is reassuring that the identification strategy works, because this fall was clearly driven by lower demand and not supply side factors in the European emissions trading scheme. The results also illustrate the important role of energy prices in the transmission of carbon pricing. They point to a significant pass-through of carbon to energy prices. This is consistent with the interpretation that the utility sector and power producers in particular pass through these costs of emission allowances to their product prices to a significant extent. And they're able to do so because European electricity markets are highly segmented and thus not subject to international import penetration from countries without a carbon price. At the same time, power sector is able to decarbonize at relatively low cost, and thus they can profit from like a higher carbon price, at least in the short run. It's very different for industrial sectors, which compete in international product markets and thus are not able to increase their product prices without losing significant market share. I perform an event study in this matter, and in fact, I confirm that the utility sector is the only sector that displays a significant increase in their stock prices after these carbon policy surprises. All other sectors tend to decrease. Higher energy prices in turn can have significant effects on the economy, both via direct and indirect channels. So, to the extent that energy demand is inelastic, Higher energy prices essentially act like a tax by reducing the discretionary income available for other expenditures. So this is a direct effect. However, there are also important indirect effects that operate via the general equilibrium effects on wages and employment. Now, to look more into these channels, I estimate the effects on GDP and its components using simple local projections on the shock that I've identified from the VAR. And in this chart, you can see the results from this exercise. We can see that real GDP also falls significantly after the shock, and the response is comparable to the one from industrial production before. Looking at the components, we can see that this fall is driven by lower consumption and investment. Importantly, the magnitude of these responses is much larger than what can be accounted for by the energy share of the economy. This suggests that indirect channels play an important role in the transmission of the shock. Having characterized the effects of carbon pricing at the aggregate level, we now look into the heterogeneous effects of carbon pricing with a particular focus on households. And the motivation for doing so is twofold. First, this will help to sharpen our understanding of the transmission channels at work. And second, it will allow us to characterize the redistributive effects of this policy, which is interesting in itself. Problem is that detailed household level data is unfortunately not available at the EU level for a long enough and regular sample. Therefore, I focus here on the UK, where such data is available and which was part of the EU ETS until last year. I will also verify the external validity of my results using data for Denmark and Spain. In particular, I've used data from the LCFS, which is the major survey in the UK on household spending. It is a repeated cross-section, and based on the last 20 waves, I compile this repeated cross-section. It has unfortunately no panel dimension, so to estimate the dynamic effects, I use a grouping estimator. And in particular, I group households by their normal disposable income. And to fix ideas, I assign them into 3 different groups: low-income households, which correspond to the bottom 25%, middle-income households, which correspond to the middle 50%, and high-income households, which are the remaining 25% at the top. Here you can see some descriptive statistics on households in the LCFS, and what I want you to take away from this figure is that low-income households tend to have a much larger energy share in their expenditure than high-income households. It is almost 10% for low-income households and only around 5% for high-income households, so almost double. Here you can see the impulse responses of a carbon policy shock on household expenditure and household income for the 3 income groups that we consider. We can see that low-income households experience a significant and persistent decline in their expenditure. In contrast, the expenditure response of high-income households is barely significant. Not only are low-income households more exposed to carbon pricing because of their higher energy share, they also experience a more significant fall in their incomes because they tend to work in sectors that are more exposed to carbon pricing. And again, these effects operating through income illustrate the importance of these indirect effects that I was talking about just before. My results also have important policy implications. In particular, they suggest that fiscal policies targeted to the most affected households can reduce the economic costs of climate change mitigation policies. And to the extent that energy demand is inelastic, which turns out to be particularly the case for low-income households, this should not compromise emission reductions. This is crucial because for a sustainable transition, it should really not be the case that it comes at the cost of the most vulnerable households. I also perform a number of robustness checks. In event studies, an important or delicate choice is always the selection of events. So I do quite a bit of robustness on that. And another thing that I want to mention is regarding the sample. So for estimation, I used a longer sample starting in 1999. But this is just to get more precise estimates, but the results are robust to constraining the sample just to the period where the ETS was actually in place from 2005 to 2018. All right, so let me conclude. In this presentation and paper, I provide new evidence on the economic effects of carbon pricing from the European carbon market. I showed that the policy is successful in reducing emissions, but this comes at an economic cost. Importantly, these costs are not borne equally across society. The policy has been regressive, at least in the past years. Now, given that auctioning is the default method of allocating emission allowances and there are significant auctioning revenues, one could address this issue by targeted fiscal policies to the most affected groups, and this can reduce the costs of this policy without compromising emission reductions. And this is it already from my side. Thank you so much for your attention and looking forward to your questions. Thank you.
Thanks, Diego, for respecting your time quota perfectly. Maybe some questions?
I have one, if I can start.
Yeah, of course, Manila.
Cool. So I was wondering about these events and in how far this could have been anticipated by policymakers saying upfront how they will vote and how this would affect your results. So I was thinking maybe you just estimate sort of a lower bound and effects could be larger.
Yeah, this is a great point. The idea is really, I mean, to the extent that the events are anticipated, if I compute the change in the futures prices, it would just be zero. So in this sense, basically, I just identify the component that is unanticipated to the extent that markets fully price all the information. Obviously, that's also one caveat, but I kind of rely here on efficient markets. Yeah.
Cool. Okay, thanks.
Thanks, Malin. Maybe some other questions? Yes, maybe I have two questions. The first one I would like to ask you is, are you considering to extend your observation periods to the more recent times, and including what we are seeing now with the discussions on the 2030 energy package, on the climate neutrality goal, on the reform of market stability reserve? So you stop your estimations at the end of 2018. So I guess you catch some discussions on the policy side of this new reform of market stability reserve, but how this will impact your results if you extend your time period to this what we are living now, especially regarding the fact that for more than 10 years, the announcements made by the EU Commissions regarding the potential reform of the EU ETS, you mentioned the backloading. We know that all those announcements had little effects on the carbon price. So I'm really interested, first, if you have identified some sub-periods regarding the impact of policy announcements on the carbon price, and then what's in your mind we observed if you extend this your period to the recent times. And the second one is more linked to what you present in the end of your article, the impacts on households. You focus only on the UK, and explain that, of course, due to the availability of data, but you know that for UK it's not exactly the same situation that in the rest of Europe. So, for instance, in UK, the electricity price to end user are mostly free, set freely. That's not the case, for instance, in France, where we have a regulated price for electricity. In the UK, there is this minimum level of carbon taxations, this price floor for carbon. So are your results transposable to other countries in Europe? And for instance, for countries where we tend to regulate end user prices. So that's my two questions.
Thanks very much for these questions, Boris. These are very important issues, and let me answer in turn, or try to answer in turn. So regarding the first one, this is an excellent point. Also, given, I mean, at the end of my sample, I catch a bit of this like recent increase, but I stopped when like the increase really started to pick up. So in a sense, it would be really nice to have this more recent period where carbon prices also have been higher, and thus the effects could even be more pronounced. What confined me when I started this project to the end in 2018 was the emissions data, which only becomes available with some lag. But I will definitely try to update this, maybe include like 2019, yeah, when this data is available, or 2020 even, because yeah, I agree it would be very interesting to have this more recent period as well. Now, to the extent that futures markets are forward-looking, maybe part of it, I mean, as you said, like these discussions or like news about this stability reserve that is very important, I may already capture because the planning started like in 2018 or something. So some of these events are in there. But I definitely agree, it would be nice to extend, to have that also in my sample. Now, to the extent that carbon prices have been relatively low for extended periods of time, especially like from 2010 to 2017 or something like that, I would expect if I have like periods again with higher prices, the results, if at all, should be more pronounced, because there may be some non-linearities that only kick in if the carbon prices are at a certain level. Yeah. And regarding the second issue of the external validity, I mean, that's a very good point. I'm in the process of like trying to get data also for other countries. I was able to verify at least the main results on expenditure by the income groups for Denmark and Spain, and reassuringly it looked very similar, but I'm completely on board with you that there is a lot of heterogeneity in Europe and across European countries. It will also be interesting to look at different countries and explore these differences. But what I've done also for the UK, if you just look at the aggregate effects on GDP, consumption, and investment, they look quite similar to the EU aggregate. So that's also something that was reassuring, that maybe it's not that bad of an exercise just to get a sense of the average effect on European households. Now, obviously, there might be important heterogeneities across countries, and definitely worth exploring this further. But the data constraints, I mean, for instance, in France, I looked into the household surveys and they're not available every year, only like every 5 years or something like that. And like the relevant surveys with expenditure and income, which is kind of what I need. And this constrains me a bit to a narrower set of countries. But would definitely be interesting to expand this further. Yeah.
Thanks for the answer, Diego. And if I may, I would like to add some extra work to your next update of your paper. You may be interested in look at the impact on not the global economy, but on the sectoral side, and how you can disentangle the global effect on the economy on the different sector, maybe using some NAS code or something like that. I'm not sure it's something which is consistent with your methodology, but it will be really nice to be able to know what are the effects on the employment and on the activity for different sector in Europe, to be something which will be really nice to have.
I completely agree. That's also on my list to do. I started with the household side because, I mean, consumption is the largest component of aggregate demand. So if you really want to understand what's happening to GDP, you have to understand consumption first. But I agree the firm side is also very interesting. And I have some interesting results also in innovation, because I used like data from the European Patent Office. And it seems that like this argument that higher carbon prices foster directed technological change in climate change mitigation technologies has some bite, because I find an uptick, even with these moderate carbon price levels that I have in my samples, I find an uptick in innovation in these technologies. And I agree, like if you look at the firm side, you could also look at investment and maybe disentangle this a bit further using sectoral classifications and stuff like that.
Okay, so a lot of work ahead. Good luck with that, Diego, and thanks again for your presentation.
Thank you.
So now we turn not completely different topics, but we are now moving to another kind of market failure with Leopod that will discuss why we need some capacity markets, capacity mechanism to complete the energy-only markets. So Leopod, the floor is yours for 20 minutes. Yeah, that's
Can you
fine.
see my screen? Okay, can you see my screen?
Yeah.
Yep. Okay, perfect. Hi everyone, thank you for having me today. So I'll be presenting my paper, which is about how to design reserve market with an application of the demand function in capacity markets. So let's start with our initial motivation for this paper. First of all, you need to understand that in our economy, there is some essential goods which are characterized by the fact that we need to have sufficient investment to produce them when needed. Otherwise, we are going to sustain a significant system cost. And this is the case, for instance, in electricity. We saw it in Texas this winter with a huge blackout cost. It's the same thing happened in California this summer, but this is also the case for medical supplies, as illustrated, for instance, by the COVID crisis. The second motivation for this paper is that we cannot fully and only rely on private incentives, such as, for instance, wholesale prices, to provide sufficient investment incentives. You have a huge reason of number for that. You have fixed cost, technical constraint, political intervention that prevent the price to give the right incentives to invest in production capacities. So one of the solutions is reserve markets, so such as capacity markets, where you allow producers to sell an availability for a future period for their investment in return for an additional remuneration. So this is well known in the electricity sector, for instance, in capacity markets, but keep in mind that what we do in this paper can be applied to other types of specific goods, such as medical supplies. The third motivation behind this paper is that it's not because that you set up a capacity market that you ensure that the trade can take place on this market. From the supply side, there is not a specific issue. You know that if you allow producers to sell a promise to be available, they are going to sell their availability. So the supply function is straightforward. But from the demand side, it's not because that you are going to set up this capacity market that the demand is going to spontaneously emerge on this market. So, think about the fact that, for instance, investment is a bit like a public good. Everyone wants to have enough investment to use electricity, but no one really wants to pay for that. So the big question that we are going to look at in this paper is who should be buying those capacities and how. So we are not really questioning if a capacity market is good or bad, but we are thinking about how we can efficiently implement a capacity market. We are going in particular to look at two different types of market design. In the first centralized market design, we are going to assume that there is a single regulated entity who is going to buy and forecast the whole level of capacity for everyone in the society, and then are going to allocate the cost on the retailers and on final consumers. On the other hand, we are going to look at a decentralized market design where you are going to force retailers and consumers to buy themselves their own capacity to cover their own future consumption. So we are still, for now, don't have a clear-cut answer on which market design is the best. You see on this map that in France or in some US states, they use the decentralized market design, but for some other states and in the rest of Europe, they have a centralized market design. So what we do in this paper, we are going to look on the overall effect of each market design on the overall economic system. The first, what I call the direct effect, is well known in the literature. Of course, if we have different demand function, we are going to have different capacity prices and of course different incentives to invest. But in this paper, we are going to look at the indirect effect of each market design. And more specifically, we are going to look at the incentives that each market design is going to give to the demand side. And we want to look at what's going to happen when we take into account the participation of retailers and elastic consumers to capacity markets. The main idea, the main global effect that we want to study in this paper is how the equilibrium on the wholesale and retail and capacity market is going to be impacted by the different market design. From a practical point of view, our comparison between the centralized design and decentralized design is going to boil down to, for the first one, how the cost is allocated to final consumers, and for the decentralized design, how retailers value at the margin an additional capacity. What we find in this paper, our main contribution is to build the first and complete and tractable model to assess various market design option effect on the economic system. The second main contribution is we are going to highlight the trade-off between the goal of having enough investment. If we simply want to have enough investment in the economy, so a simple centralized market design is optimal. We give the money to the producer, and that's all. But if we have if we want to have a more subtle management of the issue and of the electricity sector, maybe a more complex market design can bring some more benefits. But you have to be careful on the cause and the need for the capacity market, on the initial assumption, and some other parameters. What we want to stress in this paper is really you have to be careful when you think about the first best solution and the path to reach this first best solution. Because we are going to stress that the mechanism which was implemented to reach this first best can have an impact on the value of the first best solution. It can be beneficial or negative. So you have to be careful when you implement such mechanism. So I'm going to skip the contribution. I'm going to jump right into the model. So I'm going to use a very simple framework, which is well known in the electricity sector, where you are going to have perfectly competitive producer who are going to use a single technology to produce electricity with a marginal cost, a fixed cost, and a capacity. You have retailers who are going to play or not à la Cournot on the retail markets, and you are going to have some consumers who is going to have individual stochastic demand and a price elastic demand function. The main temporality of this model, to have this in mind, is that you are going to take investment decision and capacity market, not knowing what will be the future demand. However, when you enter the wholesale and the retail market, you are going to know the demand function. This is going to bring me to the first important part of this paper is what is the first best solution in this framework. So first of all, you can find the optimal level of investment simply by maximizing the expected social welfare on your system, which is composed of two parts, the off-peak parts, the off-peak social welfare and the on-peak social welfare. So think, for instance, that you have two different states of the world in your system. The first one is when the capacity level, here K, is above the quantity of the perfectly competitive market, which is simply the intersection between the marginal cost and the demand. In this case, the price is the marginal cost and the quantity is here. However, as soon as the capacity is below this quantity, then we are entering the on-peak period, so prices have to rise to have an equality between demand and supplies, even though we are in a perfectly competitive market. So the first best solution is given by this maximization of this expected social welfare, but it's simply strictly also equal to the equality between the fixed marginal cost and the expectation of this expected rent made during on-peak period. It's strictly equal, strictly the same. Okay. So this is for the first best solution. However, as I said in the introduction, electricity markets are plagued by a set of inefficiencies. in this model, we are going to use two different types of inefficiency. The first one is the price cap. It simply means that during some on-peak periods, you're going to prevent the price to be reached. So it's going to generate lower expected rent, meaning that producers are going to receive less money, so they're going to invest less. A second type of inefficiency, which is a bit more complex, is inefficient rationing or rolling blackout. It means that you cannot discriminate efficiently between high willingness consumers and low willingness consumers when you need to lower the demand. So look at this right figure. When your price is reaching the price cap, which is here, then your quantity consumed is going to be at this level, but your capacity is below. So you need to lower the demand. But because you cannot discriminate efficiently, you may disconnect people who are going to pay for this electricity, but who, for technical constraint, is disconnected. So you're going to generate another surplus loss for the society. So this is creating a gap between the market equilibrium and the social equilibrium. Okay. So those two different types of inefficiency causes the need for a capacity market to increase the level of investment. So as I said in the introduction, I'm going to look at two different market designs, the centralized one and the decentralized one. For the first one, the essential nature of a centralized demand is going to depend on the way I'm going to allocate the capacity cost onto the consumers. And I'm going to look at three ways of doing so. One is two of them is an ex-ante design, meaning that you are going to allocate the cost, whatever is the demand function, the level of demand when the demand is known. And when, for the third one, I'm going to look at an ex-post design. I'm going to say that my capacity cost allocation is going to depend on the way I'm consuming electricity during this period concerned. So let's jump to the centralized design. The first design is what is found is 99% of the literature on capacity market. It means that there is no indirect effect of a capacity market on the way I'm going to consume electricity. There is no, it's simply a surplus transfer between consumer and producer. So think about a lump sum tax. It does not affect at the margin the demand function on final consumers. In this case, there is no indirect effect, and the centralized market design is optimal given the set of inefficiency. You simply give the money to the producer, they invest, and that's all. Okay. So what I find in this proposition is that under this design, it's strictly the same as implementing capacity market or simply giving the money to the producer, you know, just like the debate versus price versus quantity instrument in the literature. So this is what I put in this graph. You simply take money from the consumers from the surplus and you're giving it to the producer to increase the level of investment. In the second market design, for the centralized case, I'm going to assume that the way you allocate the capacity cost is going to lower your demand of electricity because you increase the electricity price. So it acts just like a unitary tax. The first result that I have when I assume this type of market design is that when you only take into account the direct effect of a price cap, you're going to have always a negative effect on the social welfare at the first best investment level. So just to rephrase it, when you only have a missing money issue on your economy, it is better to allocate the capacity cost without distorting the demand. The intuition behind this result is that, of course, if you are going to lower your demand of electricity, you are going to lower the size of your welfare function. So, of course, it's going to be negative in comparison with the first case. However, as soon as you integrate the inefficient rationing, then maybe this way of allocating the capacity cost can bring some benefits. The intuition is that by lowering the demand, you also lower the occurrence of inefficient rationing of rolling blackout. So you're going to have a trade-off between having a loss due to the fact that you lower the welfare function because you lower the consumption, but you also gain because you are going to lower the occurrence of inefficient rationing. So you're going to have a trade-off when you implement this type of market design. And of course, if the gain in terms of inefficient rationing is better than the gain of lower consumption, then you are better off at the first best investment level given this market design. So we saw previously two different types of centralized demand, where you don't really care of if I consume a lot during the realized period or I consume less. In current implication of capacity markets, so for instance in the UK, they try to implement the fact that, for instance, using a market share ratio, if you consume less during peak periods or during rationing periods, then maybe you are going to be allocated less capacity cost. And we want to know, with using this third design, what is the implication of having this ex post market design for the allocation of capacity prices. And we find that in terms of effect, it's going to be a bit intermediary effect between the first one that we saw with a lump sum tax and the second one with a unitary tax. So it's a bit intermediate, but keep in mind that it can have some redistribution properties, because in this case, retailers is going to sustain also the cost, just like consumers. So we saw the centralized demand market design. Now we can turn toward the decentralized demand market design. So it's completely different. Now you have to to put yourself in the place of a retailer who is going to be forced to buy the level of capacity on the capacity market to cover its own client portfolio. So you are a retailer, you are forced to cover your client portfolio by buying the same amount of electricity. So I put it as the most simple case. You are a retailer, you make some retail profits in this equation, then you are going to have to buy your capacity on the capacity market. And then if you sell still more electricity than what you have bought in terms of investment, then you are going to sustain a penalty. Okay. So if you take the most simple case where you don't have any uncertainty, you know what is going to be your demand function in the future, then I find in this, using a very simple game theoretical model, that the set of dominant strategy is to always follow the level of capacity that you have bought on the capacity market when you sell electricity on the retail market. Okay, so just give us this intuition that you always follow the capacity level that you have bought on the capacity market. So what does it mean from implementing this simple way of thinking into the initial framework with this uncertainty, when you have to take into account the fact that when you buy your capacity, you don't know what will be the future of your consumer demand. So what I find is that you can differentiate between three different cases depending on the level of investment that there is on your system. So the first case is when the capacity level is above the quantity bought when the price cap is intersecting the demand function. So when it is the case, then there is strictly no difference between the initial framework and the decentralized one. A third case happens when you have retailers who are going to sell more electricity than what they have bought in terms of capacity. So they are going to sustain a penalty. They pass the penalty to the consumer, who are going to lower their demand. And in this case, this third case is when the level of capacity is below even at compared to the quantity which is the intersection between the price cap and the demand function lowered by the penalty. For the second case, it is a bit different because we have a bit of a paradoxal situation. You have a consumer who is going to consume at the price cap this level, but this level of capacity is here. So in theory, you should have a penalty. But if you implement the penalty system, then there is no more any there is no need for any more penalty in the system. So it's a bit paradoxal. So how you solve this issue? If you are a rational retailer, then you are going to lower your demand function so that you avoid the penalty. And this is very important because this is what we call the implicit demand response. Because of the penalty system, you want to either increase by a small amount your price or give the money to the consumers to avoid having to pay the penalty. And by doing so, by lowering the demand by this amount, you avoid having rationing on your system. So this is what is the main idea of a decentralized system, and this is one of the main reasons why in France, for instance, we implement this type of capacity market. We wanted to have, during the specific period in time, this implicit demand response.
Leopold, 2 minutes left.
Yep, perfect. So I have this I have modeled this the way how this decentralized market is going to affect the way you're going to sell your electricity. So I can deduce what is the welfare function on your market. I can deduce the profit function of the retailers, and then using this expected profit function of the retailers, I can find the demand function on the capacity market, and hence all the equilibrium of the model. Just to conclude, I don't have time to present, but this was a very general framework, but I also have some numerical illustration using a closed form solution for this model with a linear demand. I can use some numerical data from the French data, for instance. And just to conclude, what I want to stress in this conclusion is that because we provide a general framework, and the first framework to really try to analyze those different market design, what can be useful is to make some extensions of this model. For instance, when you want to have a flat rate versus price reactive consumers, and you want to know what is going to change in the model. Another one issue is information, because maybe you can state that the single regulated entity, which is going to forecast the whole level of consumption in the future, might have better or lower quantity compared to the aggregate information that retailers and consumers have on their future consumption. So using this different type of information, you might have different results using this model. Yep. Thank you very much.
Thank you, Leopold, and well done to succeed in concluding in time. So still have some minutes for a few questions. If there is.
Yeah, I have one, or actually maybe more like two, because and you already triggered that when you mentioned the extensions. So you assume price elastic consumers. I was wondering why not inelastic, which would I think be more realistic. And on that, I really like this idea of extending your work and exploring heterogeneity there in terms of consumers. Also thinking again about Diego's results. Maybe if you have low income price inelastic consumers and high income more elastic consumers, this would also raise some distributional differences between the centralized and decentralized design. So maybe some more additional insights. Yeah, thanks. Cool presentation.
Yes. For about the elastic consumer. So I don't think it really matters in terms of intuition behind the results. The fact is, actually, yes, it can change a lot because I wanted to look at, for the decentralized design, if you assume 100% of inelastic consumers, the decentralized design doesn't work at all. So of course, if you want to implement a decentralized capacity market, you need to assume some elastic consumers. So just to let this model be simpler, I assume 100% of elastic consumers. But of course, this model was without a capacity market. It's Leopod in 2016 used the same model with different type of consumers, and it varies the ratio of consumers. And I plan to see what's going to happen if you have different type of consumers. Thank you.
Someone else, maybe? I have a few questions myself. Maybe I will pick one. If we assume that there is a asymmetry of information between the regulator and the retailers, isn't the decentralized system, the decentralized design, the most obvious one? If we assume that there is no perfect information on the regulator side, we do not know what is the actual level of demand, what it will evolve in the future, etc.
Yeah, actually, but it was the initial motivation behind this paper. First, to know maybe the regulator is less informed, but what I think is that maybe the retailers is more informed on the future consumption, but you're always going to have a trade-off between the fact that they might have better information, but they can act strategically, they can have some market power. So by having a single regulated entity, it can provide some stability, I would say, on the markets. So having more informed retailers, it might be beneficial. So you really need to calibrate correctly your market design. This is what I was saying in my introduction, is when you have more complexity with a decentralized market design, surely in theory it can bring some benefits, but you really have to be careful, for instance, with the value of the penalty when you set up this market design. When I was working on this paper, I was thinking that, wait a minute, maybe you can conceptually understand this debate on centralized and decentralized a bit like when you implement a carbon tax versus a quota market. And you see it when I was modeling the decentralized market. I found some work when you have this producer who needs to buy in advance some quotas, and then they have the realization of their production, their demand for their good. So, and they can sustain a penalty because they don't buy enough quota of CO2 on the market. And so it's a bit the same. And this is why I said for the capacity cost allocation on the centralized design is a bit like a tax. In fact, you are going to tax consumers so they can and give the tax to the producer, so they increase their level of investment. So you see, you can find in the debate again for the tax, it's stability, but maybe you are missing the real value of the externality. And with the quota market, maybe you introduce some more complexity, but you give some more flexibility. So you see, this is why I was thinking when I was working on this paper.
Okay, always a good thing to remember this old debate between price and quantities. Maybe some more practical question. When we look at the latest auctions on the capacity markets on the UK and in France, we saw that even both systems are really different in terms of conceptions and in terms of the way we draw this demand function. Prices are really closed. Okay. How we could explain this market outcome? Our systems are quite different. Yeah. The way we build these capacity mechanisms are completely different, but prices are really close. It's a true question. I'm really wondering why.
I don't have in mind. I don't have the number is mine, but I would say it's when you look at capacity markets, it's very different from the spot market where you have huge uncertainty. You have different drivers. I think in the capacity market you still have the same order of magnitude. So even though you're going to have a different demand function and different demand function, the supply curve is going to be fundamentally the same, I think. So what I think it's very important for when you look at capacity markets, is what I wanted to show in this paper, is really to be careful on the indirect unknown effect of this capacity market. So maybe it's going to affect differently the electricity prices in the long term. It's going to affect the way you are going to pay as a consumer your electricity. So to maybe on the short run with a direct effect, it's the same. So you might have the same price, but the way you're going to set in place indirectly the capacity market might have other implication. Yes.
And I think one of the big question is which kind of capacity mechanism is the most suitable to an electricity sector mostly dominated by renewables. And I think the way we develop capacity mechanism for now is not probably the right way to do regarding what are the goal and what are the objectives of our sector. But
I usually, as usually in the electricity sector, we tend to overlook the demand side of electricity. And just like similarly to the renewables, I think we tend to overlook the demand side. And this is one of my questions that I'm trying to tackle in this paper is to say, wait a minute, what's happening when you really want to take into account the demand side on the capacity market and just not simply giving the money to the producer so they can invest.
That's the feeling I have as well. So good, thank you once again, Leopold. And now we turn to our last presenter, to Federico. Yes, you're still there, Federico, nice. So Federico, the floor is yours to present what happened in Guatemala and why it is so hard to make people connecting to the grid.
Thank you, Boris. Oh, well, first of all, I'm sorry for wearing the face mask, but I am at the university because I wanted a reliable internet service. So this is the trade-off. I have to I must
Don't be
wear
sorry.
a mask. So, well, okay.
Yeah, that's good.
Okay. So this topic from the power reliability, it was first motivated by policy implications. In the first term, as you can see there, a lot of money is spent worldwide in expanding the grid or maintaining the grid network. And when I first, when I started this research from Guatemala, which is a Central American country, small Central American country, I read an article in the newspaper online from Guatemala, which called my attention, and it says there was a woman who was claiming she lived in an isolated town in the north of Guatemala, which is very poor, and she was saying that they didn't need a light bulb. They need teachers, they need doctors, but they didn't need that grid expansion, that grid network. So that called my attention in the sense of, well, what are we doing in the terms of trade-off and the opportunity cost of these large investments, especially in small countries, in low development countries? And well, how do we spend this money in grid expansion, and especially if that goes to people in terms of electrification and in terms of benefits? So I will focus on, especially on the second aspect of the standard development goal, number 7, which is reliability. And in that sense, reliability, it is also in the terms of the urban and rural gap. If we see the data on electrification access from Guatemala, electrification access is, well, I may live in a town that town has electrification, perhaps the school, or perhaps just 1 or 2 households, but I do not have electrification. And that is the difference between electrification access, my neighbor, my town has, and the difference between electrification rate, which is focused if I do have a grid connection. So if we look at the rural Guatemala figures in the national population census in 2018, if we take into account the World Bank data, electrification access was 93%. But if we see how many households were really grid connected, just 77% were connected. 12% are still using candles, and small 6% are using solar panels. So my main motivation, the empirical question is, how does power reliability affect rural households' willingness to grid connect? And the methodological approach that we will use is basically using 2 household data sets and 1 official record of the quality of the firms that supply energy into the rural Guatemala setting. And we focus on power quality as a barrier to electrification, as I said before, and potential heterogeneous effects over municipalities according to past performance. That means, in other words, well, not only perhaps current quality affect rural household willingness to grid connect, but also past performance. And then, well, why Guatemala is a good country to focus on? Well, this is a bit of background in the history. They finished a civil war in 1996, and they experienced a boost in rural grid expansion. In fact, the electrification access grew from 55% in 2000 to 93% in 2018, as I said before. And how did they do that? Well, especially they liberalize the market, they sell some state-owned utility firms, and they get some loans. And with that background, with that money, they could expand the grid so fast in so few years. And the second issue is that, well, the residential sector energy consumption is based mainly on firewood, just 5% on electricity, and that means a high potential demand electricity. And there's a large local urban-rural gap in Guatemala, which means in terms of income, in terms of education, in terms of poverty. For example, in 2014, the poverty levels in the Guatemala capital city, Guatemala City, was 30%, while in the north of the country was 70%. And this gap is also seen in the quality of energy, of electricity supply, which is, there are more outages in the rural setting, 35% more in duration, and in frequency, 14%. So for the literature review, many papers are focused on the industrial sector. For example, the paper of Alcott in the American Economic Journal review, talking about productivity in India, also on firm sales, on average unit costs, on some investment on backup generation for firms when they get, you can sense the grid connection fails, they have a backup generation. And the household level, the majority of paper are focused on electrification benefits, and they take for granted that quality is always present. And there's a paper that I would like to cite here is from Louise Grogan in 2018 in the Journal Economic of Development from the Guatemalan case. She analyzes another period of the history from 2000 to 2011, and she says that, well, this main grid expansion allowed many people to get connected, and especially for women, there was a positive impact on income, and especially on labor force that they could get into the labor market. Then in the recent years, there has been an interest on reliability in itself, but sometimes always in connection with the benefits of electrification. And there's another branch of the literature based on willingness to pay. And those papers are very interesting, but they have another methodological approach. And well, in fact, many of them, they say the same. People are willing to pay more for better quality services. So, but how electricity quality supply is measured, and this is my key point, many of these papers, they are based on surveys and on questionnaire that they are in the service. So perhaps they have questions using a Likert scale. How comfortable, how do you think your power supply is from 1 to 5, from 1 to 10? How many outages did you have the last week or the last month? So mainly they rely on subjective, they rely on the respondents and the memory of the respondents. So they are prone to measurement error. And this is the main contribution of this paper. We are using an official and objective reliability measure of quality at municipality level. Then we focus on quality as a barrier to to electrification. And then we provide empirical evidence in Latin America, in an upper middle income country. And although it is considered by the World Bank as an upper middle income country, there's much inequality in income between the rural zone and the rural zone, as I said before, and we can consider just the rural zone as a low-income country, as a low-income zone, sorry. So far, to keep the ideas clear, I want to focus on, as I said before, on the effect of reliability, on the quality. And this is a map of Guatemala. In the left, we have regions. Regions are just a political division, but with no political power. Political power do have municipalities, which are in the graph of the right. And in the graph of the right, I have the three main utility firms that are in the country. We have the ORSA in the east part of the country, the OXA in the west, and this light blue zone is for EXA. This central part is the Guatemala metropolitan area. Here in light blue also, you can see it. And this is mainly zonal distribution. The key point here is that the OXA and the ORSA provide to the 92% of rural households in the whole Guatemala. So I will keep an eye, especially on these two firms. And how do I measure quality? Well, quality, as I said before, this is by the CNEE, this official agency in charge of watching the quality in the country. And I use this measure, which is SAIDI, is the System Average Interruption Duration Index, which is mainly an average number of hours that a household in a municipality does not have electricity. So looking at this figure, I have in the y-axis the number of hours per semester that an average household does not have electricity. So the larger the number, the worse is the quality. And as you can see here, these two lines are from the OXA and the ORSA, and this is from EXA. I'm just looking at rural quality, but the figure is very similar if I look to urban. In this, I will exploit this spatial variation because I have, hopefully, I have in the first data set, I have data from 2011 where the quality is, we can say, good, and I have data on 2014 with quality is not as good as before. So why this sudden shift could have happened? Well, there's some evidence of managerial problems. We can say first the OXA and the ORSA was sold first from a company called Unión Fenosa to Actis Group in May 2011. And then it was later resold again in 2016 to the actual owner, which is Energuate. Energuate is the company that owns these two sub-companies, let's say, the OXA and the ORSA. Another possibility is there was a proximity of a tariff agreement expiration in 2014, and this could delay some important investments. And there's also anecdotal evidence in local press blaming for this lack of investment of these two firms. There could be another explanation. It could be generation constraints. Well, it is not the case for Guatemala. There is no load shedding, and outages are more prone to be caused by distribution constraints, especially in the way that the grid network is designed. Then it also could be thought, is there a reverse causality problem? Perhaps an expected consumer's growth rate could have caused that bad quality. And if we see this figure, although you can see these long bars, and one could think that, okay, it could have been this unexpected growth rate, but if we look at the average annual growth rate from these firms, EXA has a larger number of growth rate of consumers. The OXA and the ORSA have a similar number, and as we saw before, EXA did improve while the others did not improve in quality service. And then another possibility, perhaps high prices, and this could entail unpaid bills and theft, and that could have caused that bad quality in service. And in this graph, we can see This is the social tariff that pays almost the Guatemalan households. And these bars are saying the subsidy that the government pays to the poorest people. So the poorest people, which are almost all the rural households, they always pay 50 cents per kilowatt. So it doesn't matter how much is the really cost of energy, because these people will always pay the same. So that's why as the price goes up, the subsidy goes up, but the people are always watching the same price. So fortunately, I will not care about too much about the price of energy. So the tariff scheme, as I said before, there's a social tariff. It changes every 3 months. It is settled by the official commission, but it takes into account the cost of energy. So they can change the price, firms can change the price. And there is this in the contribution, as I said before, is in fact the subsidy that the government pays to the poorest household. There's a tired up subsidy. So from 1 kilowatt to 60, they pay 50 cents. From 61 to 88, they pay 80 cents, and then they pay the social tariff. As they are, as I said before, too poor, their consumption in kilowatts is very low, so that's why they pay these 50 cents. And this is just a picture of how the firms were at 2014. As you can see there, I want to stress just 2 things from this table. This, the per capita consumption, you see 68 and 79 kilowatts per month, and compensation in quetzales, which is the currency unit of Guatemala. The OXA and the ORSA were having many troubles in the service that they provide, and the number of cutoffs, they are claiming a lot of rotation in clients, in customers. So far, let's go to the model. I have, as I said before, 2 ways of facing this question of reliability. The first one is using the ENCOBI, which is the National Survey of Guatemala. I have 2 rounds, 2011, 2014. I have this dummy at household level, which is the question that they have to ask, which is the main source of lighting that you have. And if they answer the grid network, that equals to 1. And if not, it's 0. And there is here, alpha 1 captures the effect of 1% change inside a department level, because unfortunately I do not have the household and municipality level. Then household control variables, also department control variables, region fixed effect, and time fixed effects. And the other data set that I use, using a more granular level, because I have municipalities. I have 2016 municipalities. This is the census. And again, I have the grid connection at household level. And then the quality is at municipality level. Well, I will skip this because of time constraints. Okay, let's see the first results. Using the ENCOBI, using this time variation and spatial variation, a 1% reduction in SAIDI, so a better quality, it will entail 23% of 23 percentage points of more probable to grid connect. And well, the other control variables, this is just a subset of control variables. If the head of the household owns the house, it has a positive effect. Real income, as expected, has a positive effect. And this CDD that I haven't explained yet is the cooling degree days. Alcott usage and many other in the literature uses this weather demand driver, which means, well, the hotter is the weather, probably the more demand of electricity there will be in that region. So this is the main results in this repeated cross-section. And the standard errors are clustered first at primary sample unit, and then I also cluster at department level. As they are so few, there's just 19 departments, I made a wheel a wild bootstrap replication, and results remain the same. Then the second is with the census database, and again, the results are, the sign is negative, so quality matters, but effect is smaller. Well, there are some potential issues I want to focus on here. Well, what will happen if this quality shift, in fact, was not fully exogenous? So I make an IB strategy, and this IB strategy is using rainfall as the instrumental variable, as you perhaps may have seen in the news. Recently, there have been floods and landslides in Guatemala, which affects really many services. Well, I use two potential sources of rainfall data, from first local weather stations and then NASA satellite images. In this map, in the left, there's the quality levels in each department, and in the right, you can see the spots, the dots are the weather stations, and I collapse that data at department, and I have the mean of rainfall in each department. So, and this, I want to focus just, this is Alta Verapaz department. In this department, just a fact, an issue, it has a lot of hydroelectricity plants, but it is the department with the lowest level of grid connection in the whole Guatemala. So here we have the IB regressions, and the only model that is strong and we have enough statistical evidence of not being weak is using the model that I said before in the COVID setup with weather station, which have more variation and more, more variation. And again, the effect is significant, and it is almost 40%. Then another potential issues. Well, perhaps I have a measurement error calculating SAIDI at department level, because so far I just make a simple average to collapse quality data at department level. So one could think that this is not good enough. So I have now a weighted measure. I weighted by the number of households that has each municipality inside the department. And the results remains, although they are lower. The other robustness check is now using again the census database. For time constraint, I will just focus on these placebo tests. Well, quality, in fact, is a matter for grid connection, but it's not an issue for water and for garbage service, as expected. Lastly, just some heterogeneous effect. I will focus on this. Does past performance matter if I look into the time span from 2015 to 2018, and I just make a dummy variable for bad reputation? If it equals to 1, if the number of times that I will just, sorry, I will explain this a bit further. I have this figure, SAIDI levels in 2018. Each spot is a municipality quality. And this line, 14 hours, is the number of hours that the official government says that you have to, that's the maximum of SAIDI that you have. If not, you are punished. So there are some municipalities that always are defaulters. This is the number of times in 5 years. 4 times they default, 3 times defaulted, 2 times, and so on. So I will focus what will happen in the defaulter zone, in the defaulter municipalities. And here are the heterogeneous effect. If the first group are those who are non-defaulters, quality matters, 3% of reduction. And the second column is these defaulters municipalities. So first, it could be that there's no effect, but if we take into account the interaction between bad reputation and the dummy for bad reputation, the results will say, okay, the quality matters for those who have good reputation, and then for the group of bad reputation, if we make the sum of these two coefficients, they are statistically zero. So what does it say? Okay, if you are if you have bad reputation, it doesn't matter what you are doing now. You must do a much effort, you have to do more, because not only you are a defaulter, but you are always a defaulter. So you have to better off in your quality statements. So to conclude, quality matters. There you have now some figures in terms of what will have been the new connections if they had better quality in terms of new connections, 69,000 households or more, depends on the estimation strategy used. And then results also suggest an heterogeneous effect of SAIDI over municipalities. Conditional, you are a defaulter, current quality matters unless the municipality has bad reputation. And the policy implication that this has is that efforts to expand the grid line to rural areas should be analyzed in concordance with actual power grid quality levels. And if we take into account the Grogan paper, as I said before, this has a huge effect in terms if the quality improves, electrification improves, and that will make the better life for the rural households of Guatemala. Well, thanks for your attention.
Thank you very much, Federico, for bringing us this topic of grid access in Guatemala. Any question from the audience? Yes, Madeline.
Yeah, I can start again maybe. Yeah, two questions. The first one is, can you say a bit about the cost of electrification or the cost of gaining grid access? Like, I mean, so having bad quality
the
grid
cost for
access,
the household?
Yeah. I mean, like for me, having bad quality electricity would be better than having no electricity. Yeah. What are actually the costs? Why would I not always adopt? And and the second one is about the IV. I was wondering whether rainfall could have a direct effect on electricity demand, because I don't know, it's raining, it's dark, I want some light, I want to have ventilators if it's combined with humid weather or something like that, and therefore could have a direct impact on network access demand. These are two questions.
Okay, thank you very much. Regarding the second one, well, in fact, I would think the same as you, but not for the income level that I am thinking of. And because they don't have they are so poor that they do not have those possibilities. Let's say, okay, it's raining, it's dark, and I will watch the TV. In fact, if you see the figures, in the whole country, I don't remember very well, but just 14% of people do have a TV. So in the whole country, and taking into account the urban. So it's not a chance. And regarding, it's not an option, sorry. And regarding the cost of electrification, the law says that if you are 2,000 meters close to any installation of the firms, you don't have to pay anything for that connection. And the picture the table that I show you, it also makes a sense regarding the cutoff number of households. That means if 20% of the actual people that are connected to the grid, they decided not to pay because of the quality, that is saying us something. It is not just the cost of connection on itself, the fixed cost to connect, but also in terms of they feel that they are stolen, in a sense. I saw in the news from the newspaper, people were claiming that they were stolen. They were stolen by the companies, in the sense that they are paying for something that is not good.
I see. Okay.
And Federico, is there any a policy in Guatemala, either at national level or at the level of municipality, that try to target those DSO and try to improve reliability?
Yes, there has been mainly two. The first one that I saw from the ministry is the change in the way that the grid line is built. They try to go to a radial design And this radial design, in terms of outages, is if you have an outage in a zone, it doesn't mean that the whole zone will get out of light. That's an issue. And the second one, the punishment that the firms have when they do not accomplish with the law. That is also a way of trying to tackle this issue.
Okay, so very interesting. Thanks again, Federico. And since we are now running out of time, thanks again to all of you for your presentation. That was really nice. And see you tomorrow for the second session of the Best Student Prize, the same place on the web and the same hour at 5 p.m. Have a nice evening. Thanks again to all.
See you tomorrow.
Bye-bye.
Thanks. See you tomorrow. Bye-bye.
Bye.